Hello. I just wanted to start the conversation about graphing log functions. Again, if you remember how we started this chapter that we're working on, that we started looking at exponential functions and then we started solving exponential equations and things like this. So we're just essentially repeating the process for logarithms, although this is coming at the end of our time with logarithms rather than at the beginning. I figured you needed a break from graphing, but anyway, I just want you to see what these look like. We can talk about the domain and range. We can talk about how logarithm then affects the asymptote that we found in exponential functions. So I'm choosing just very basic ones. As you look at the sheet, there's no add-ons to it. It's not like log base 2 of x minus 3 or something like we had before, or there's no coefficient out front, or there's nothing that's added or subtracted outside the log. We're just talking about a bunch of parent functions and what they look like. And I want you to see how changing the base from 2 to 3 to 1/2 to 10 to e, how that affects the shape of the graph. So I'm going to try to be very consistent with my labeling, so that we can pick out the differences between all the graphs, see what that base is going to do to the shape of the graph. All right, so we won't need to make a table of transformations like we did before. Trust me, I have a sheet on that for us to do. But for right now, I just want you to get comfortable with just the regular base and no transformations. So what I'm going to do, again, we've gotten somewhat comfortable with this notation. I'm going to remind you that it means the same thing as y. And I'm going to remind you that really the equality doesn't have to be on the left side here, that we can put it on the right side and rewrite this as log base 2 of x equals y. I prefer it when we have logs like this because it helps me remember how to change it into an exponential form. So if you remember, when we change something from logarithmic to exponential form, the base of the log becomes the base of the exponential, and then we just flip-flop these two. So it becomes 2 to the y equals x. All right, so you shouldn't feel uncomfortable with that exponential form, but you should feel maybe slightly weirded out by the fact that our variable, which we usually call x, is not up there, but it's a y, and x is what the equation is solved for. And that is a significant concern, and it is going to impact how we graph them. So I'm just going to start to make my xy table. But what's going to be different is, instead of picking the x values, I'm going to choose the y values because x is what I'm solving for and y is part of the equation right there. So normally where in exponentials we would do -2, -1, 0, 1, 2. I'm going to put them over here instead. So this is going to be -2, -1, 0, 1, 2. Right? And again, that comes from the fact that our y is not the thing that's solved for anymore. It is part of the exponential, and x is what is solved for. And so we're just going to reverse the position or the job of which variable is the one that we choose. Normally we choose the x and get the y. Now we're going to choose the y and get the x. Right? So when I do that, if I put -2 in for y, this is going to ask me for x to find 2 to the -2. Right, well, 2 to the -2, hopefully you remember that's 1/4. Then when I put y in up here, 2 to the -1st is 1/2. When I put 0 in for y, 2 to the 0 is 1. When I put 1 in for y, I get 2. When I put 2 in for y, I get 4. All right, so again, the reason I'm choosing y this time is because when I rewrite this logarithmic function as exponential, this y is what we're raising 2 to the power of. And so we end up choosing that. It's much easier to think, how could I get a 2 out of this, right? What would I have to do in order to get 2 as an answer? And think, oh, I would have to raise it to the first power. I might start choosing things that I can't even solve. Like let's say I said, oh, what happens? How will I get 6 here? Well, 6 is never going to show up in this column because it's not 2 to any power. So we have to be very particular about what we pick. If we choose the x's, we have to make sure it's a power of 2. So it's just easier to pick the exponent. All right, having said that, let's start making our graph. And again, this is going to be what it looks like every time because I'm going to try to be really consistent. But I know that for my y values, I need to have a nice even mix of both positive and negative, right? I've got up to positive 2, down to negative 2, and so I'm going to be consistent with that. That I will always try to put that y or the x-axis right in the middle so that I get both positives and negatives for the y values. And again, I realize that it's a slightly uneven, and I'm sorry about that for my ADD friends, or not my ADD friends, my perfectionist friends. Okay, and then I'm always going to put, in these problems, I'm always going to put the x-axis right here because there are no negative x values that I'm going to get out. I'm raising a positive number to some power and I'm never going to get a negative. All right, so let me just go across here and I'm going to go up to, just for consistency's sake, I'm going to skip by, I'm going to count every one of these as, every 2 I'm going to count as 1. So each block is going to be a half. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, and 9. We won't need to go up that high. And in future ones, I'm just going to do 2, 4, 6, 8. So if you are working ahead, that's what you could do. All right, and then for our x values, I'm going to do the same thing. Each block is going to be a half. So half 1, half, no, each block is going to be a half. So then half 1, half 2, half 3, half 4, and same thing with the negatives down here. Okay, so let's plot. So when I'm going to start with these because they'll be a little bit easier. When x is 4, y is 2, so we've got up here. When x is 2, y is 1. When x is 1, y is 0. When x is a half, y is negative 1. So here we're at half and negative 1. And when x is 1/4, y is negative 1, 2. Negative 2. This is where it starts to get a little tough. All right. So I'm just going to connect it with a nice smooth curve right here, like we did with our exponential functions. We could, if we wanted to, also do positive 3. Because this is then saying 2 to the 3rd power is 8. That might give us a little bit of a target to shoot for up here. If we did that. All right. Now, when we're talking about domain and range, again, if I were to continue up in this direction right here, if I were to choose negative 3, so 2 to the negative 3rd, that would be 1/8. If I were to choose negative 4, that would be 1/16. If I were to choose negative 5, that would be 1/32. What I want you to notice is that while this continues, this x value continues to get closer and closer and closer to 0, there is no way it's ever going to reach 0 because I will just continue to cut in half and half and half. It will never reach 0 because as small as it gets, it will still always be positive. This is the same thing we found with the exponentials, except what was happening was the y values were getting closer and closer and closer to 0 instead of the x values. So we will notice that it never goes to 0. It also will never get negative. No matter how many times I multiply a 2 together, be it a 2 with a positive exponent, in which case it's continuing to grow, or a 2 with a negative exponent, in which case we're showing decay, it will always stay greater than 0. All right. So as we look at this and we say, okay, well then what's the domain and what is the range? All right, so I'm going to just squeeze them in here. Domain. Domain talks about what the x values look like. Again, I have nothing graphed over here, but we could continue this on like this, and it wouldn't matter because the graph is never going to show up here. Again, it's going to hug this y-axis right here and continue to get closer and closer to it, but never touch it and never cross it. So when we say what x values are we going to get out of this function, it will never be 0, it will never be negative. And so we're going to say that the domain is x, because again, domain always has to deal with x. X is strictly greater than 0. All right, we'll never get the graph showing up on this side in the second or third quadrants. All right, another way to write that again with our interval notation is to say 0 with a rounded off bracket, because we're not allowed to include 0, up to positive infinity. It's going to continue to grow farther and farther in this direction, so we'll have all x values greater than 0, but none 0 or less. All right, for the range, I should do this in a different spot because I'm going to regret this in a couple minutes. All right, for range talks about the y value, or the y values, all right? So we can literally pick anything we want, all right? As you can see, I kept going lower and lower here. I'm going to continue to get x values that correspond with that, all right? And I can continue to grow, you know, in this direction. You can see that there is an upward trend in this direction, so it's going to continue off to positive infinity, and there's very clearly it's decreasing without bound in the negative infinity direction, right? So this graph is just going to spread infinitely upward and infinitely downward. So this range is negative infinity to infinity, or all real numbers. Okay, last thing is the asymptote, and I'm going to put it right here. Clearly I wasn't thinking of making a video when I was designing this worksheet. So the asymptote is that line which the graph never touches, or it approaches as either x or y gets infinitely large. All right, so in this case, we have a line here that our graph is approaching, but is never going to touch, right? And so this time we say, hey, actually, when we did exponential functions that looked like this, we had a horizontal asymptote, but when we're graphing logarithms, they look like this, where we've got a vertical asymptote. So our asymptote is going to be at 0. It's on the y-axis, and the way we write that is we call it y equals 0. If you remember, nope, lying. It's x equals 0. It is which axis it hits. So it's hitting the x-axis as it goes up. All right, you might say, well, Mrs. Taylor, it's hitting the y-axis everywhere. Yeah, but if we slid it over one, it would just be hitting the x-axis. So this is an x equals line, not a y equals line. All right, in class on Thursday, what I'd like to do is draw both of these on the same graph. Draw log base 2 of x and draw 2 to the x, so that you can see how they're related shape-wise, and also the similarities and differences between their domain, range, and asymptotes. So we will take a look at that on Thursday. All right, let's take a look at log base 3 of x. Again, I'm going to cross out that f of x and remember that it just means y. And then instead of putting it to the left of log base 3 of x, I'm going to put it to the right of it, so that I get that form that makes it so easy for me to convert it into exponential form. So the base here, the 3, becomes the base of the exponential, and then the x and the y switch positions. All right, so we're going to make our table again, choosing y, not x, and finding the value of x. So here we're going to get x and y, -2, -1, 0, 1, 2. All right, if I start down here, this says 3 to the second is what we put in place for x, so that's 9. 3 to the first is 3. 3 to the 0 is 1. 3 to the -1 is 1/3. 3 to the -2 is 1/9. again, I'm going to graph the same way. All right, so you can go ahead and do this too. I'm also going to put 9 because I need a 9 on my graph. And then I've got 1, 2, 3, 4. Sorry, I don't want to write the numbers here because you're going to mess that up. All right, but here I'll put -2, and then we've got -4. All right, so let's just plot. At 2, nope, sorry, at 9 it's 2. So we're going to be up here. At 3 it's 1. At 1 it's 0. At 1/3 it's -1. This is where things start to get really hard to graph. At 1/3 it's -1. Nope, that even looks like 2/3. At 1/3 it's -1. At 1/9 it's, you're not even going to be able to tell the difference between where my dot is and 0. It's so close. All right, so then we draw a nice smooth line through them. A nice smooth curve. Sorry, it's not a line. All right, it's going to continue on infinitely far in that direction. Sorry if I'm missing, if this stuff wasn't in the screen, I'm sorry. I'm sitting as I'm writing because it's easier to do that. Okay, so hopefully doing this a second time was easier. We just fill these in, and again, we're putting them in the position of the y, and we're getting out the x value. Right, so what I want you to notice is, look at these two graphs. Again, I graphed them exactly in the same spot. I made sure that this line went right across here. We have got our y-axis in the same position. What does changing from a base of 2 to a base of 3 do to our graph? All right, hopefully you say, well, in one sense, nothing. It still looks like that same thing. It's going to start down really, really steep here in the low negatives and come up. It's crossing at x is 1. It's crossing the x-axis at x equals 1. And then it's kind of just doing a turn off to the right, and it's going to go on forever. Right? So that part of it, the log family-ness of it, the log resemblance is there. But notice that here at 2, we're able to get much higher, because how many times do we need to multiply 2 together to get 8? 3 times. Here, when we got out this far, it only took 2 times for us to get to 9, right? And so we're going to find that as we increase the base, it takes less and less numbers of y as our exponent to get to this value right here, right? When we get to log base 10 down here, at 10, it's only going to be up at 1 because we only need 1/10 to get that high. So that value is going to keep decreasing as we increase the base. It's going to happen much faster that we achieve that value, and so our y value is going to be our y value is going to be much lower, right? So we would say that as the base increases, the graph gets less steep. It flattens out much faster than it does here. It's still not wildly steep here like it is here, right? This part of the graph is starting to flatten out already, not like here where it's super steep. But when we compare the two of them, this is much flatter earlier, or it achieves a flatness that this doesn't quite achieve so soon. Okay. Let's do one last thing here before we move on, and that is talk about domain, range, and asymptote. Okay, so again, there's not much difference between these two graphs. Sorry, just realized I didn't focus it. There's not much difference between these graphs in terms of where the x values go. again, they get closer and closer to 0. This one gets closer to 0 faster than this one does, but they still just get closer to 0. But it's never going to cross over here. It's never going to hit 0. It's never going to go into negative territory. So again, the domain is 0, rounded off, indicating it's not including 0, all the way up to positive infinity. And then likewise, its range is always going to be all real numbers, because it's always going to have this same pattern of heading towards negative infinity or towards n infinity as it gets towards its asymptote, and then heading larger, higher in the opposite direction, right? So this is always going to be all real numbers. Maybe you remember from when we were doing the exponentials that we said domain is always all real numbers, and the range will depend on where the asymptote is. Hopefully, maybe you're thinking, oh my gosh, this seems like the exact opposite. Range is always going to be all real numbers, and domain is going to depend on where the asymptote is. And that is true. And the reason is because they are inverse functions of each other. And so their domains and ranges will flip-flop. All right? Okay, let's take a look at this one, and then I think we'll just maybe have to look at the others another time, because this is getting on the long side. All right, so again, I'm going to cross this out, and I'm going to write it as equals y over here. And then I'm going to rewrite this in exponential form, which says 1/2 to the y power equals x. And I'm going to choose y equals -2, -1, 0, 1, and 2. And then we're going to figure out what x's will give us those y values. All right, so if I put -2 in for y, the negative is going to flip the fraction to make it a 2, and then we're going to square it. So we'll end up with 4. And then here, when we put -1 in for y, the negative will flip that, making it a 2. When we put in 0, that's going to give us 1. When we put in 1, we'll get a 1/2. And when we put in 2, we get 1/4. So you might be thinking, I feel like I've seen those values before. Yeah, up here. All right. So these are actually the reciprocals of what we have down here. All right. So that's going to change the graph in a related way to what we had up there.
What's the song by Adele?
So we do 1, 2, 3, 4, and 1, 2, 3, 4. And then we'll go over and count the same way that we did before. So 1, 2, 3, 4, 5, 6, 7, 8. All right, again, I'm going to put, actually I'll put -3 up here to give us that 8 to help us find, get a better trajectory here. All right, so when x is 8, y is -3, 1, 2, 3. When x is 4, y is -2. When x is 1, y is 0. When x is 1/2, y is +1. And when x is 1/4, y is +2. All right, we draw a nice smooth curve between them. And we get that. So you can see all your paper at once, but I can't fit both of them on the screen very well. But you'll notice that they are basically mirror images of each other. If we look at this log base 2, it starts out low and it goes up high, and all the y values are the exact opposite of what they are down here. All right? Here we have at 8, it's -3. Here we have 8, it's +3. Here we have 4 and it's -2. Here we had 4 and it was +2, right? So they really, quite literally, are mirror images of each other. All right. Let's talk about domain, range, and asymptote. So domain, again, As soon as we see what that asymptote is right here, that line that is stopping the graph from moving any further in one direction or the other, we know that's where our asymptote is. We know that is the beginning or ending of our domain, depending on what we do with our transformations. So here we're going to say the domain is 0 to infinity, not including 0. Our range, again, we can see that it's going to continue to go down towards positive infinity. It's going to continue to go up towards, it's going to go down towards negative infinity, up towards positive infinity. So it's negative infinity to positive infinity. Don't think that because you read it from left to right and it goes infinity to positive infinity that you should reverse these. It's always, as we read from left to right, it's least to greatest. Even if, as it occurs on the graph, it occurs in the opposite direction. All right, so because negative infinity is the smallest value that we achieve, we write it first, even though it occurs as x is getting really large, not closer to 0 here. All right, and that's why the positive infinity comes up second. All right, and then the asymptote is going to be still this line, x equals 0. Shoot, I realized I didn't write it in this last one, x equals 0. Okay, I'm going to ask you at some point to do log base 10, and then we will do natural log together. All right? Okay, that's it.